Almost every living thing on Earth depends on oxygen for the support of life. Let's see for ourselves just how important oxygen is. Both of these jars contain oxygen in the air, so the mice are normally active. But if we introduce a little more oxygen, that mouse becomes much more active. Meanwhile, the other mouse is using up his oxygen and gradually becomes sluggish and inactive. Now, as pure oxygen enters the jar, watch his almost dramatic recovery. This property of oxygen in supporting life is used in many ways, for example, in high-altitude flying and in medicine. Another great importance of oxygen is in the burning of fuels. The candle flame is bright and full in the air of the room. As the oxygen in the air is consumed by combustion, the flame dies down. But more oxygen restores it, and the candle burns vigorously. We have seen that oxygen supports the combustion of fuels, and how important it is to living organisms. Fortunately, the Earth's crust is almost half oxygen. Oxygen occurs in the free state in the atmosphere, and in many chemical compounds, such as water, minerals, and plant tissues. Air is about 1/5 oxygen and 4/5 nitrogen, with traces of other gases. Air can be liquefied by applying great pressure at a very low temperature. This liquid air is very cold, colder than minus 194 degrees centigrade. As the liquid oxygen-nitrogen mixture warms up to minus 194 degrees, the nitrogen boils, going back into gas. After most of the nitrogen has boiled away, we have nearly pure liquid oxygen, pale blue in color. Liquid oxygen boils at minus 182 degrees. The extreme cold of the liquid air destroys the elasticity of the rubber ball. This is mercury, a metallic liquid element at ordinary temperatures. Mercury freezes very quickly at this low temperature. And it is frozen solid enough to use as a hammer for this small nail. Oxygen for commercial or medical use can be produced from liquid air, as we have seen. When nitrogen boils away, the liquid oxygen can be vaporized and stored under pressure in steel tanks. Another way of producing pure oxygen can be shown by this electrolysis apparatus. The H-tube is filled with water containing a little sulfuric acid to make it conduct electricity. When electric current is introduced here, the water is decomposed into its elements hydrogen and oxygen. The decomposition of water produces twice as much hydrogen as oxygen by volume. 2 atoms of hydrogen and 1 atom of oxygen make up each molecule of the compound water. That's why we write the formula of water H2O. We have seen an electric current decompose the compound water and release oxygen. Now we shall observe the effect of heat on another compound, mercuric oxide. Heat decomposes the mercuric oxide, releasing the oxygen gas and leaving the pure element mercury. When we test, we are sure that's oxygen. We have experimented with a typical oxide, a compound of oxygen and just one other element. Now, let us examine a more complicated compound called a salt. Here is potassium chlorate, a compound composed of 3 elements, potassium, chlorine, and oxygen. The middle test tube contains only manganese dioxide. The third test tube contains a simple mixture of the first 2. As the temperature rises evenly in all 3 test tubes, we discover an interesting thing. At about 200 degrees centigrade, oxygen is being evolved from the mixture. From the manganese dioxide alone, no oxygen is being evolved at the same temperature. And from the potassium chlorate alone, only a little oxygen is being released. Since the manganese dioxide released no oxygen, it was not changed by the heat. But we see clearly that the manganese dioxide altered the decomposition of potassium chlorate when mixed with it, causing the rapid release of much oxygen. From this, we can state a rule. Substances which alter the speeds of chemical reactions but remain unchanged at the end are called catalysts. In this experiment, manganese dioxide in the mixture was the catalyst. We have decomposed compounds to release elemental oxygen. Now, we shall make compounds, or oxides, by chemically uniting pure oxygen with another element. First, we ignite a piece of a metallic element, calcium. Then we ignite a non-metallic element, sulfur. Now we let both burn in pure oxygen. Chemically, the oxygen is uniting with the burning elements to form oxides. We find that these oxides are soluble in water. And when we test with an indicator, litmus, we discover that metal oxides dissolved in water give basic solutions, while non-metal oxides, like that of sulfur, give acidic solutions. We have seen the decomposition of water to produce the elements hydrogen and oxygen. Here is a simple apparatus with which we shall reverse the process. Suction applied here draws air past the hydrogen flame. When the oxygen in the air combines with the hydrogen, water vapor is formed and condenses on the ice-filled test tube. Here is another demonstration of substances burning in the presence of excess oxygen. Soaking a cotton ball in liquid air gives a heavy concentration of oxygen, much more than in the surrounding air as the liquid air evaporates. Watch this gunpowder. Rapid oxidation reactions which evolve light as well as heat are called combustion reactions. Here is another type of rapid oxidation reaction that can be highly explosive. The tin can holds a candle and a funnel filled with fine dust-like powder. Any fine dust, such as coal dust or flour, will produce the same result. Now, the rubber hose and bulb will allow us to blow the fine powder loosely into that space where the candle is burning, and it will oxidize. But oxidation at that speed gives an explosion if the heat and gases of combustion are confined. Some oxidation reactions, such as rusting of iron, are very slow, too slow to generate perceptible heat. However, the slow oxidation of some substances will result in what is called spontaneous combustion. Here we have soaked a bit of cotton in linseed oil, turpentine, and Japan dryer, which are often found in paint. At the start, the thermometer shows room temperature. But within an hour, if the heat of oxidation is not dissipated, but allowed to accumulate, the temperature will have risen to a dangerous 350 degrees centigrade. Now, if a whiff of air gets to it, a fire results. That's the part that oxidation plays in causing fires where greasy, oily rags are carelessly thrown into a wooden locker or a drawer. If we observe and experiment, we'll have a better understanding of the physical and chemical world we live in and the importance of the simple element, oxygen.